Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Hello. Video on. Okay, this is lesson 14, Similarity. Classwork example 1. This is a quick lesson and a lot of just talking and explaining what we've learned in the previous lessons. It says that we said for figure A in the plane, it must be true that A is similar to itself. Describe why this must be true. So, there are several different transformations that map A onto itself, such as a rotation of 0 degrees or a rotation of 360 degrees. Okay, so that would map its figure onto itself. That's what they mean by A being similar to itself. A reflection of A across a line and a reflection right back achieves the same result. Okay, that makes sense. A translation with a vector of length 0 also maps A to A. And the direction doesn't matter because if your length is 0, direction is a point. There is no direction either. Okay. A dilation with a scale factor of 1 maps A to A. And any combination of these transformations also maps A onto A. Therefore, A must be similar to A because there are many similarity transformations that map A to itself. This condition is labeled as reflexive because every figure is similar to itself. Okay, example 2. We said that for figure A and B in the plane, so that A is similar to B, then it must be true that B is similar to A. Describe why this must be true. So what we're saying is if A gets mapped to B, then B has to get mapped onto A. Okay, yeah, that kind of makes sense. This condition must be true because for any composition of transformations that maps A to B, there is a composition of transformations that can undo the first composition. For example, if a translation by vector xy maps A to B, then vector yx will undo that transformation and map B back onto A. A counterclockwise rotation of 90 degrees can be undone by a clockwise rotation of 90 degrees. We just keep rotating back and forth. It's kind of like a washing machine agitator. A dilation by a scale factor of r equals 2 can be undone with a dilation by a scale factor of r equals 1/2 because 2 times 1/2 is 1. And if you look back up at example 1, a dilation of scale factor 1 will map something onto itself. So there you have it. All righty. Let's get this stuff out of the way. Where's my other? There is an example 3 somewhere. There it is. Okay. So based on the definition of similar, example 3 says, how would you show that any two circles are similar? So a circle with different centers but radii of equal length. If two circles have different centers but have a radii of equal length, then the circles are congruent. And a translation along a vector that brings one center to the other will map one circle onto itself, or onto the other, I mean. Okay, B, what if we have circles with the same center, but the radius is different? The radii are different. If two circles have the same center, but one circle has a radius r and the other has a radius r prime, then a dilation about the center with a scale factor of r equal r prime divided by r maps one circle onto the other so that r of r equals r prime. So the scale factor of r will bring us to r prime. And circles with different centers and radii of different lengths. If two circles have different centers and radii of different lengths, then the composition of a dilation described in B and the translation described in A map one onto the other. I will bring in an example for that. All right, so here it is. If two circles have different centers, here's center one, here's center the other, and the radius is different. Obviously, this circle is way smaller than this circle. Then the composition of a dilation described in B, same center, but one circle has the radius r and the other r prime, same center, then the dilation with a scale factor of r prime over r will map one onto the other. So what they're saying is if we took a vector and translated the big circle to the little, moving this big circle on top of this one, and then dilating it r prime over r, then it would shrink the big triangle down to the same size as this this circle. It'd shrink this circle down to the same size as this circle, and the centers would be the same. Okay, so that's what they're saying here. Page 2, example 4. Suppose triangle ABC will map onto triangle DEF, and that under the correspondence, corresponding angles are equal and corresponding sides are proportional. Does this guarantee that triangle ABC and triangle DEF are similar? Preserving angle measures and proportional side lengths. We've already shown that if two figures, example triangles, are similar, then corresponding angles of equal measurement and corresponding sides are proportional in length. Check. This question is asking whether the converse of the theorem is true. We know that correspondence exists between triangle ABC and triangle DEF. What does correspondence imply? Well, the correspondence implies that the measure of angle A equals the measure of angle D, the measure of B equals the measure of E, and the measure of angle C equals the measure of angle F, and side DE is to AB as EF is to BC as DF is to AC. That's what correspondences means. All right, so we will show there is a similarity transformation taking ABC to DEF that starts with a dilation. How can we use what we know about the correspondence to express the scale factor R? Okay, well, since the side lengths are proportional under the correspondence, then R equals those proportions. Okay, let me pause right here and give an example. So let's bring in a triangle. And how about a right triangle? So if I draw this triangle and then I draw this triangle here, and then we will label it A, B, C, D, E, F, 90, 90, 45, 45, 45, should put degree symbol, I guess. 45 degrees, 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 degrees. Okay, so if this is, I don't know, 3, and this is 4, and this is 5, then this is 6, and this is 8, and this is 10. So we have angle A equal to D, A is equal to D, B is equal to E, B is equal to E, and C is equal to F. And DE, so if I take this DE over AB, so now I'm doing this right here, DE is 6 over AB, which is 3, equals EF, which is 10, over BC, which is 5, equals DF, which is 8, over AC, which is 4. Well, 6 divided by 3 is 2. 10 divided by 5 is 2. 8 divided by 4 is 2. So this is a scale factor mapping ABC triangle onto triangle DEF with R equal to 2. So if that's the case, since the side lengths are proportional to the correspondence, then R equals this. So that's that right there. Okay, so let's continue. The dilation that takes triangle ABC to DEF can have any point for a center. The dilation A to A prime, B to B prime, and C to C prime. So that triangle ABC is similar to triangle A prime, B prime, C prime. So what they're saying here is if I now take a ray, let's use blue. No, let's use purple. And actually, let me get a ruler. Let me do it with a ruler instead. So if I put this ruler right there on A and run it through D like there, and then I draw a line like so, and then I take the ruler and put my line going through F, and I'm off the screen just a little. All right, let me fix this just 1 second because I want to show this. Okay, so I move the triangles over so my center of dilation is on screen. So then I move this to here, and I draw a segment from D to A and beyond. And then I do the same for C and F. And then I do the same for B and E. And as you can see, these all cross right here. And that is our O. So what this is saying is we take this one step further and say that, move this out of the way. Where were we? Right up here. I had to move stuff around, so that's out of it. Okay, so this is what we were saying. The dilation takes ABC to DEF, can have any point for a center. So there it is. So if I change the size of either of these triangles, then the center is going to move. The dilation maps A to A prime, which I'm calling D, B to B prime, which is E, C to C prime, which is C prime would be F. So that triangle ABC is similar to triangle A prime, B prime, C prime, or in our case, DEF. How would you describe the length of A prime, B prime? A prime, B prime is equal to our dilation times AB, but in this case, A prime, D prime is DE. So all I would do is say DE equals R times AB in this situation, which is the same as this. They're just calling their triangle A prime, B prime, C prime. And up here, they called it DEF, so I don't know why they switched back. But anyway, we take this one step further and say that A prime, B prime, which is DE, equals R times AB, which equals DE. Okay, now they're saying it. DE over AB, which equals DE. Similarly, B prime, C prime equals EF, and A prime, C prime equals DF. So A prime, C prime would be here. So they're basically saying this is A prime, this is B prime, and this is C prime. And therefore, AB is mapping to A prime, B prime, which is the same as DE. Hopefully that didn't confuse you too much. Okay. All right. All right, so in this example in your book, this is what they're leading up to. And what this is would be taking triangle ABC, dilating it so it's the same size as this, and then rotating so it would land, or there might even be a reflection in there too. All right, so anywho, let's move on. Part B says, Joel says that the sequence must be a dilation and 3 rigid motions. But Sharon is sure there is a similarity transformation composed of just a dilation and 2 rigid motions. Who is right? Well, let's take a look. Okay, so let's start off. We're going to use this diagram here. Let's start off by moving an angle to a corresponding angle. And so if I get my ruler, I think I got rid of it. I take my ruler and draw a segment from B to B prime. Like so. Okay. Then let's pick a point O that would get that dilation down there. So I need to measure from B to B prime, which is 4.5. Okay. So I'm trying to think how I'm going to do this. Okay, so we need a proportion here. So let me measure corresponding sides. So let's measure AB. So if I measure AB, it is 3.567. So I'm going to write that over here. AB equals 3.7 centimeters. So AB prime is going to be a proportional length. It's going to be shorter, and we need to find the proportion R, which is the side over the side. So if I line this up and measure A prime, B prime, it looks to be 2.4 or 2.5. So A prime, B prime equals, let's call that 2.5. All right, so the original is the big one. The image is the smaller, so R is less than 1. So I put A prime, B prime over AB to find my ratio. So now R is going to equal A prime, B prime over AB, which equals 2.5 over 3.7. So if I go into my calculator, those aren't very good numbers. Clear 2.5 divided by 3.7. It's about 2/3. So let's just say it is 2/3. So let's say R equals 2/3. So it's a 3:2 proportion. Okay, so now going back to my B to B prime length. Hopefully you're following this. Trying to be as accurate as possible. B to B prime is 4.5. So it's kind of, well, it's a segment. I wouldn't put, let's just put segment and get rid of that. B to B prime is 4.5. Well, 4.5 is the larger distance. So I need the smaller distance, and 4.5 is to some length as 3 is to 2. So if we cross multiply, we get 3x equals 9. Divide both sides by 3, and we get x equals 3. So if this is 4.5, then I want my point of dilation to be 3 away from B prime. So if B prime is at 4.5, 3 would be 7.5, which is right here. So that should be my O. So from here to here is a length of 3, and from here to here, did I do that correctly? I don't think so. That's going to be 7.5. So from here to here, if that is 1 and this would be 2, that'd be a scale factor of 2 over 1 to the whole thing. No, I'm not doing this correctly. So 4.5 is to x as 3 is to 2. 4.5 is not my 3. This is a little confusing, so just bear with me. I'm going to explain something. So we take part over whole equals part over whole is what we're trying to do. Come on. All right, so some value OB over O prime B prime, or B, O prime B. There is no O prime. It's B prime O. So let's go O B prime. So O to B over O to B prime equals 3 to 2. Okay? OB, but B to B prime is a distance of 4.5. So the B over B prime is a distance of 4.5. This is interesting. All right, let's bring some algebra into this. So B to B prime is 4.5. Okay, B to B prime is 4.5. So 4.5 plus some value x equals OB. So OB is 4.5 plus x. 4.5 plus some unknown length will get me from B to O. Okay, B prime plus B prime O. So my B prime O is my x. So it's going to be 4.5 plus x divided by x equals 3 over 2. Okay, cross multiply. 9 plus 2x equals 3x. Subtract 2x from both sides and get x equal to 9. So if x equals 9, and that's my B prime to O, I need to measure from B prime to O is a length of 9. Let's see if that works. So 9 is right here. So let's move this O to here and get rid of this O. And extend, or let's delete that and redraw it. So then if I put my ruler on B prime going to O, like so, then I put my ruler on O, rotate it around to A. No, it doesn't. Okay, there's no need to do all this calculating. So watch what's going to happen. This just came to me here. So let's not do that. It should have worked though. I'm not sure why it didn't. All right, so if I just, no, that's right. I'm sticking to my guns here. This is right. A does not have to go through C. So there we go. And then rotate to C and go through there. So there is my point O. Whew. B goes through B prime, A does not, because we haven't rotated yet. That's why these aren't going through. So if I scale this down now, if I take my, no, not that. Control Z. Let me take my square, rotate it. All right, so let me just think about this. I want to slide it on a ruler so that I make parallel sides with AB. So I put that on AB. I bring my ruler up. So if you're doing this on paper, this would line up like so. Then you would slide your ruler up until you are at B prime. And you would draw a segment from B prime up to A. And that is my A prime, B prime. Okay, and then we're going to do the same with BC. So if I put BC like so, rotate my ruler and slide it up against my square, and then move the square over. Oh, I went the wrong way. How would we do this? Oh, okay. Let me rotate it the other way, like so. This would be so much easier on paper. So if you're doing this on paper, so much easier. All right, so let me put that there. All right, so I want to move BC up to B prime, but being parallel to this. So how would we do that? Okay, so here's how you would put the protractor or the square. And then I would rotate this up, push this up against it like so. Slide, I don't want to rotate, slide it up, pretending that you're up against this till I get to B prime, and then draw a segment. What color was I using? Blue. From B prime over to the other ray. Okay, so now I'm done with that. Rotate, put this here, rotate, draw. So there's step one. I just made A, B, C, or not congruent, but similar to this one, okay? Actually, it's congruent. I was right saying congruent. All right, so then what can I do with that? Can I just rotate it? So then if I try to rotate, let me make it all one piece. Okay, so if I rotate this, can I get, so it is a reflection as well. So as you can see, rotating it, so dilating it and rotating it, get me to this point here. So now I can share sides, but then I'd have to flip it over. So Joel says the sequence must require a dilation and 3 rigid motions. Oh, a dilation and 3. Actually, no, it's a dilation and 2. So we dilated it, we rotated it, and then we're going to reflect it. But let me think about that. Dilated it. Then can we get this? No, we can just reflect it. So that B prime stays right where it is. We could find the line of reflection, which would look like going through B. So we could find, I'm not going to take the time to do it because we've done it and done it and done it. But if we take perpendicular line segments that bisect a point of reflection or line of reflection, then we would be, I think we can just dilate and then reflect. All right, so I'm thinking we could do it in all 2 total. Dilate and then 1 rigid motion over reflection. Okay, enough of that. Page 3 brings us to the end of lesson 14. Not one of my favorite lessons, but anyway, review the lesson summary and go to your problem set.